So this lesson is going to look at moles and balanced equations. So in the previous lesson, what we looked at was how we could use calculations in order to work out if we had a mass of a particular chemical, how many moles that was, or if we wanted to measure out a particular number of equivalents or number of moles of a chemical, what mass that would be. And we had two equations. We had mass equals number of moles multiplied by the gram formula mass, which was M equals N times GFM. But we also had number of moles equals mass divided by gram formula mass which was N equals M divided by GFM. Those were the two equations we had. But chemistry rarely looks at just one chemical at once, and we're more likely to have a chemical equation. And in a chemical equation, you're going to need to know how many equivalents of one chemical are needed for every equivalent of another chemical. And more importantly, you need to be able to predict how many equivalents or how much mass of product you're going to get. And to do that, we use these equations, but we also look at the chemical equation. So I'm going to start with one chemical equation. We're going to start with carbon reacting with oxygen, and that produces carbon dioxide. Now this equation is balanced. We have one carbon on each side and we have two oxygens on each side. I'm going to put on my state symbols. So we know, if we look at these, we have one equivalent of this, one equivalent of this, and one equivalent of this. What that means is that's 1 mole of carbon is needed to react with 1 mole of oxygen, and it will produce 1 mole of carbon dioxide. Now, where moles and balanced equations come in is, well, what happens if I don't have 1 mole of carbon? What happens if I have 2 moles? If I have 2 moles of carbon, then what we can do is look at this ratio and predict how many moles of oxygen we will need and how many moles of carbon dioxide we will need. So if 1 mole produces 1 mole, 2 moles will produce 2 moles. And if 1 mole produces 1 mole, 2 moles will produce 2 moles. Now that's the most simple version that we can have, where it's 1, 1 and 1. You're not always going to get that. And importantly, what we call this looking at the numbers in front, we call that the molar ratio. The molar ratio. It's nothing to do with teeth. Molar just related to moles. And so that is, whenever we look at the equation, that is just looking at the numbers in front of each one. And remember, if there isn't a number, it's 1. So what we'll do now is we will look at another few equations, and we'll look at using the molar ratio. So we'll stick with reacting things with oxygen, but this time we'll react hydrogen with oxygen. And when hydrogen reacts with oxygen, we get H2O. Now, if we want to balance this equation, we've only got 1 oxygen on this side, but we've got 2 on this side. So we need to multiply it by 2. We've got 2 multiplied by 2 hydrogens, but we've only got 2 on this side, so we need to multiply that by 2 to get a balanced equation. Now what we can do is we can write out the molar ratio. So we know that 2 moles will need 1 mole of oxygen and will produce 2 moles of water. So now, what happens if we only have 1 mole of this? If we have 1 mole of hydrogen, well, the easiest one is to look at which one is the same. Well, 2 moles of hydrogen produce 2 moles of water, so 1 mole of hydrogen will produce 1 mole of water. But what about oxygen? Well, we needed half the number of moles of oxygen compared to hydrogen. So it's going to be the same. We're going to need half the number of moles. So it's going to be 0.5, or half a mole. Now, what if this time we want, in our chemical reaction, we want to make 8 moles. We want to make 8 moles of water. How many moles of hydrogen and how many moles of oxygen are we going to need in order to do that? Well, for every 2 moles, we need 2 moles. So these two numbers are the same. So these two numbers are going to be the same. So we're going to need 8 moles. For every 2 moles of water, we need 1 mole of oxygen. So that's half. So what we need to do is half that. 8 times a half is 4 moles. So that's where we get different ones. And we'll just try one more, bit more complicated example. I'm going to take aluminium, react it with oxygen, and this time we have Al2O3. Now, to balance this, we need to do that. This is more complicated. We've got 4 moles. We have got 3 moles. And we have got 2 moles. What if we want to just make 1 mole of this? Well, we look at the molar ratio. So 2 moles needs 4 moles of aluminium, so that is multiplying by 2. So we just multiply by 2 here, and we end up with 2 moles. And then what about oxygen? Well, from 2 to 3, that's multiplying by 1.5. So we need to multiply by 1.5, and that's 1.5 moles. And so you can see, by working out the ratio, the molar ratio in the equation, we can then use that ratio to work out, if we change one of the moles, how much we'll need to change of every chemical. Now that is the starting point. What we need to be able to do now is use this molar ratio and use mass and moles. So there are two ways that we can do this. So we'll take this as our example, carbon plus oxygen going to carbon dioxide. First thing we do is we write out our molar ratio, 1 to 1 to 1. Now this time, the question might be, if 24 grams of carbon is completely reacted, how many moles of carbon dioxide are produced? So if 24 grams of carbon is completely reacted, how many moles of carbon dioxide are produced? Well, with carbon, we've been given a mass. With carbon dioxide, we're wanting moles. So what we need to do is get them both into moles. So we need to work out how many moles 24 grams of carbon is. That will give us our number here for how many moles of carbon. And then we can use this ratio to say how many moles of carbon dioxide will be produced. So, remembering our equation that moles is equal to mass divided by GFM. The GFM of carbon is 12. That's just from looking at the periodic table. So the number of moles is 24 divided by 12, which is 2. Now we know molar ratio of carbon to CO2, so we're just looking at these two, it is 1 to 1. So if we do it that way, we know that we have 2 moles of carbon. So if we've got 2 moles of carbon, they're the same number, we must have 2 moles of CO2. So that is, our moles of carbon dioxide must be 2. So we'll do a second example of one of those. And this time we will do H2 plus O2 going to H2O. And we need 2 and 2. So in this case, the question might be, if moles of water were produced, what mass of oxygen was needed? So we're going to start out doing our molar ratio again. But we need to remember we're dealing with water and we are dealing with oxygen. And oxygen, we're wanting mass. So we don't need to talk about hydrogen at all. We just need to know that oxygen is 1 and water is 2. Now this time we're starting out, the information we've been given is the number of moles, and we are needing to turn that into a mass. So if we're starting with moles, we're going to look at the molar ratio first. So the molar ratio of oxygen to H2O is 1 to 2. We have been told that we have 6. So that means to go from water to oxygen, we're needing to divide by 2. So 6 divided by 2 gives us 3. So we have 3 moles. We need 3 moles of oxygen. And we need to find out the mass. And the equation is mass is equal to number of moles multiplied by GFM. Now the formula of oxygen is O2 and the GFM of O2 is 32. So our mass is going to be 3 multiplied by 32, which is 96 grams. So 96 grams. So in this one, you can either be given moles and asked to work out mass of another chemical, or in the first example, you were given a mass of chemical and to work out the number of moles of another chemical. And the way to link it every time is using the molar ratio, which you can tell immediately. Now the final stage, the hardest type of question, is what happens if they give you mass of one chemical and ask you to work out the mass of another chemical? So we're going to come back to this equation, carbon plus oxygen, going to CO2. And this time, if 6 grams of carbon is fully reacted, what mass of CO2 is produced? So this one, we're starting with a mass, 6 grams of carbon, and we are being asked for a mass. So at no point in the question are the words moles, is the word mole or moles used, but we're going to have to use our knowledge of moles in order to answer this question. So just like before, we're going to look at the molar ratio. Now in this case, we only need to look at carbon and carbon dioxide. Now carbon, 1. Carbon dioxide, no number in front of it, it's 1. So the ratio is 1 to 1. So we know whenever we have 1 mole of carbon, we will produce 1 mole of CO2. So now we need to work out how many moles of carbon. So N is equal to M divided by GFM. Now the GFM of carbon, I'm sure you could work it out yourself, but I'll just give it to you. It is 12 grams. And so whenever we do this equation, we have 6 grams. The GFM is 12, so that gives us 0.5 moles. So we have 0.5 moles of carbon. Now we know that every 1 mole of carbon produces 1 mole of CO2. So that means we will make 0.5 moles of CO2 because it is 1, 2, 1. So we're going to make 0.5 moles of CO2. But that's not enough. It's asked us for what mass. So now we need to take this value and turn it into a mass. So this time we have got mass is equal to number of moles multiplied by GFM. Now the GFM of O2 is 32 grams. So we fill it in, we know that the moles is 0.5. The GFM is 32, and half of 32 is 16 grams. So in this question they asked for mass and then said what is the mass produced. Doesn't mention moles, but we need to use that molar ratio in the middle so that we can relate quantities of chemicals to one another. We'll do one final example to Na plus O2 goes to Na2O. So we've got this, and for this one, the question is going to be if 46 grams of Na react with excess O2, and all that means, if we say excess O2, it means that all of the sodium is going to react. What mass of Na2O will form? So again, I'm going to look at our molar ratio first. It is 4 sodium and it is 2 sodium oxide. 4 to 2. You can, if you want to, you can simplify that down, but it's okay. We'll just keep it the way it is. Now we have 46 grams of sodium, and we are then asked about the mass of sodium oxide. So we've got a mass, we started with a mass, but we need to use moles in order for them to talk to one another. So firstly, we've got a mass and we're working out moles, N equals M over GFM. The GFM of sodium is 23. So what we have is 46 divided by 23, which is 2. So that's 2 moles of sodium. Now we know that the molar ratio is 4 to 2. So if we have 2 moles, we're going to need to divide by 2. Oh, sorry. Which gives us 1 mole. So we are going to produce 1 mole of sodium oxide. Now we're going to use M equals N times GFM. I will need to work out the GFM. So Na2O. We'll do a box here. Oxygen, there's 1, so that's 1 times 16. Sodium, 2 times 23. So that's 16, 46. When we add them together, we get 62. So whenever we're doing this, we're going to use 2 multiplied by 62, which gets us 124 grams as our final mass. So with a question like this, it's always look at the molar ratio, work out moles, use the molar ratio and turn it back into your mass. So what we have looked at today is how to use a balanced equation to produce a molar ratio. And then we looked at using the ratio if we change the moles of one chemical, how that affects all the others. We then looked at some questions in which we were given a mass of one chemical and had to work out the moles of another chemical. And so we used a calculation that allowed us to work out a number of moles. Then we used our ratio to work it out. And then finally, we looked at equations where we were given a mass of one chemical and asked to work out the mass of a second chemical. And to do that, we work out moles, we then use molar ratio, and then we turn that number of moles into a mass on the other side. So that has been using moles and balanced equations. Thank you for your attention.